Good morning, everyone. Hopefully you can hear me clearly. My name is Giuseppe Scatigno. I'm an associate at Hawkins in our Bristol office in England. And today, as part of the marine series, I'll be discussing all things corrosion, focusing on hull corrosion. Briefly about Hawkins, we have a number of regional offices in the UK and also offices around the world, located strategically in the southeast of Asia, which allows us to react quickly whenever there is a claim that needs our expertise. We have a large number of experts that have expertise in just about any scientific and technical topic. We work in the marine area in things like cargo, liquefaction, but also because of the expertise that we have in things like fire materials, chemistry, biology, we are able to bring that expertise in all aspects of the marine world. And in fact, today I'll be discussing how material science and corrosion together with metallurgy can help with any marine claim that you might have that include things like hull and machinery, also cargo spoilage when it comes to metallic cargo. So to keep this interesting, I'll start with assessment of our corrosion, and today I will be presenting a number of case studies that I've worked on in the past. This was a double hull chemical tanker that had been built in 2008, which suffered widespread corrosion of the hull. This was discovered in November 2023. And we were instructed effectively to try and understand and quantify how much of this corrosion damage could be attributed to potentially issues with the corrosion protection system that all seafaring vessels are equipped with, or to do with a specific event that the owners had discussed with the insurer, which was a grounding event that occurred in 2022. There was widespread damage found to the hull, but also to the rudder and the propeller hub, which we were asked to look into. And we were told that there had been an issue with the corrosion protection system, the ICCP. The ICCP is Impressed Cathodic Current Protection system, and effectively it is what allows our hull to always be protected while we go into seawater, which, as I'm sure you're familiar with, is quite aggressive when it comes to corrosion. The field of electrochemical engineering has been able to engineer a situation in which the hull is protected while it's going at sea. And this is done by the use of a sacrificial anode, a sacrificial material, zinc, which is applied onto the hull and looks like so. And on top of that, we impress a current. Now, what you can see here on the left-hand side is effectively kind of a visual guideline of where you might be passive, therefore you might be protective, and where you might not be protective, which means that your hull is actively corroding, releasing ions into the sea. And by applying a current, we can effectively move up and down this graph, putting our metal in a situation where this is protected from corrosion. However, if this is not done correctly, issues may arise. So I visited the dry dock in which the vessel was being repaired to carry out UT testing ultrasonic thickness gauge testing of the hull to understand how much of it had corroded, and compare it with the survey that had been carried. And we knew that on average, corrosion had spread to the majority of the hull and had corroded to about 40% of the initial thickness. So that is a significant amount of corrosion, and one that we not normally see on a vessel that is well protected. It was important to try and establish a timeline to understand exactly when last time a survey was carried, in order to understand how corrosion could have evolved and with what speed. So I received a number of documents from the owner and from the insurance that allow me to look more into these details. And as part of the site investigation, I also looked at other components that suffer significantly. Now, the propeller hub here might not look like it's sustained a significant damage, but actually in the sealing phase, I found some localized corrosion that unfortunately meant that the propeller hub had to be scrapped, because we could not ensure that localized corrosion would have not kept burrowing into the hub after it been repaired. So I reviewed the damage, both the general corrosion damage, which is the corrosion of the hull, and the localized one in areas like the rudder and the propeller hub. And I collected samples for of both the oxide and of the underlying metal, and we'll discuss why later. I also saw firsthand the ICCP system on board, and in order to try and understand if it'd been wired correctly, if everything was as expected, and then compare that with the information that I received from the owners of the vessel. Now, all you need to know about this graph is that if you are in between the yellow and the green line, your hull is happy. Your hull is adequately protected, it's not corroding. If we are below this lower threshold, the metal is effectively exposed to the seawater as if it was bare metal, as if we were not protected. And we might think that if we go above this green threshold, we might have better protection, because more is better. But unfortunately, that is not the case, as we'll discuss in a moment. I calculated that since the previous survey, we had exceeded 1 millimeter loss of metal per year, which is effectively equivalent to bare metal being exposed in seawater. So effectively, as if we didn't even have painting, a coating, which is on all hulls. And this might have already been significant in June 2023. Now, why is it important that we don't exceed the higher threshold as well as the lower threshold? Is because if we exceed the higher threshold, we go into a process known as spalling. So what can happen is that effectively, by overprotecting the metal, we allow the protective coating on the metal substrate to be removed. And then at that point, not only when we are in an area where we are not protected against corrosion, we don't even have a coating that we can rely on to slow down corrosion. So by looking at this, at the data, at the thickness measurement carried out on site by myself and by the surveyor before me, I was effectively able to understand that the corrosion that was suffered by the hull of this oil tanker, chemical tanker, was to be associated by about 80% with the ICCP malfunction that you could see in this graph, where we have largely erratic behavior of the current, which suggests that we do not have a normal back feed system, but we had effectively most likely manual intervention from the crew that was trying to rectify loss of current by dialing up the system, possibly without fully understanding that really high voltage and current is not necessarily the friend of the hull. I was also able to apportion the damage that the propeller hub had seen to the grounding, and therefore I was able to help the insurer into apportioning the claim that the vessel owner had brought forward, and effectively in minimizing the event of the grounding itself, which yes did possibly strip some of the coating, but effectively did not erode the majority of the hull, and all of that had been done afterwards by the lack of appropriate current protection. As I said, I also kept some specimens from the hull and from the oxide of the hull, and that was done deliberately to try and future-proof the technical investigation against possible claims that there were other factors at play. For example, what if the steel that had been used for the hull itself had not been up to the right standard, or what if the vessel owner could claim that the vessel had been in water that were particularly corrosive while at port for whatever reason, or by doing bulk characterization. This is actually coupled plasma. We can effectively tell exactly what composition of metal we're looking at, and we're able to compare that with the standard. And by doing SEM and scanning electron microscopy and energy dispersive X-ray of the corrosion oxide, we can then tell whether or not this has been contaminated, for example, by really acidic or really caustic solutions that may have expedited the corrosion. Therefore, we were able to then prove that this did not happen, and therefore that all of the corrosion that we see was due simply by the lack of appropriate protection. Then where does corrosion come in? How can we help with marine claims, not only when we talk about hull and machinery, but also when we talk about marine operation in general? For example, cargo, here you see these are austenitic stainless steel sheets that have they've been ready to be sent to the purchaser, and they've been lashed, that they've been placed together in such a way that they should not corrode in transport. But this does happen occasionally, and by looking at the different types of corrosion that we see, how these have been stored before and during transport, we can help with determine whether the corrosion that we see can be due to how the cargo had been transported. We know that often salt water can provide cross-contamination, and that can exacerbate corrosion. But there is a number of things that we can do to understand where that comes from. For example, there have been a case recently I worked on a pylon where we were able to show that the pylon had collapsed because of how the paint had been applied, as the substrate had not been worked on correctly. We need to achieve a certain level of roughness so that the paint can be then well adhered. And so we're able to differentiate between, for example, a normal process that has happened because of normal weathering, or whether there has been something that has been done wrongly at the beginning. And we're able to differentiate also on how things have been stored. So corrosion sometimes can look like it's just a normal process, everyday process that cannot be stopped. But actually, for example, in the case of that austenitic steel sheets, we know that often they can be overprotected. The incorrect ventilation is provided. So, for example, if your cargo hold is closed and there is no way of ventilating and absorbing moisture, then moisture will stick to your cargo. And if there is any issues with saltwater contamination, which inevitably there will be when we are having operation at sea, we can again increase the rate of corrosion, and by the time the cargo reaches the final destination is unfortunately already degraded. Often we also see issues with fretting corrosion that comes from incorrect lashing of the cargo together. So we can see damage like so. Here you can see almost pits that have been created on the metal surface, and with the help of visual inspection and microscopy, we can determine whether or not the corrosion that we see it is indeed due to cross-contamination, for example, or like in this case, by fretting corrosion, which is a type of erosion corrosion, which does not really need a very aggressive solution to be present. Another interesting example of cargo spoilage is cross-contamination. This was train cargo that was going from a port in Southeast Asia to Australia. The trains were pristine, ready to effectively be put on track once they arrived in Australia, in the port of origin. By the time they arrived in Australia, when they were inspected, they effectively looked like this. They were heavily rusted, heavily corroded. Even the electrical copper conductors appear to have failed in a large percentage, and the owners of the cargo were left scratching their heads and trying to understand how this had happened. Hawkins was instructed to look at this claim, and what we discovered was that the trains were not the only cargo that had been transported at that time. The train had been transported alongside some nickel ore. Now, why is that problematic? The two were not even in contact with each other. The two cargoes were completely separated. However, what had happened is that what the port of origin that loaded the cargo was not aware of is that nickel ore often contains sulfur, because it's extracted from rocks that contain sulfide using ammonia. Now, both of these chemicals are rather problematic for the trains. The sulfide or the sulfur contains the sulfide, which becomes volatile, can then attack the panels of the train, which were made in a grade of stainless steel, while the ammonia is highly corrosive for copper and brass. So it would have degraded the conductor of the electric wires. Therefore, the incorrect storage did not only degraded the shell of the train, but also its ability to be operated correctly. And like we did in this claim, we often are involved in salvaging. How much of the cargo that we're looking at, say with the austenitic steel sheet or with the train, can be salvaged, can be repaired, how much of it has to be scrapped? And more often than not, you might be told that all of your cargo needs to be to be scrapped, to be sent away or to do something else with it, to be recycled. But actually, that's not always the case. There is things that we can do, that we can advise on as expert in contamination in metallurgy, on what you can do to effectively minimize the amount of the cargo that has to undergo that significant level of repair. And yeah, as I said, there is a number of things that we can help with, a number of things that we can help with considering when the cargo is transported, on how and why he arrives at the destination the way that it is. Again, other things that we deal with are also all sorts of marine operation, including ports operation. In this case, we had the wire rope failure of a crane, and we were instructed to try and understand what may have caused the failure of this rope, which, as you might imagine, can have a cascading effect on the safety of the workers around it, the damage to the cargo that was being lifted. In this case, we went to site and analyzed the wire in its entirety, both the lubricant that is used as a shield for moisture, whether that had degraded or not, and how effectively the wire had failed. So I carried out investigation both visually on site and then taken samples with me to analyze them under optical digital microscope to try and understand what phenomenon may have caused that failure, and, as you might imagine, reason why this example is here. Corrosion was involved. In this specific case, we had fatigue corrosion. As you can see here, we have this, they're known as beach marks, which effectively show the initiation point of your failure, from which then over several cycles of loading and unloading, you can get your wires to fail. And after a single wire fail, more and more of that load is carried by other wires until a number of them fail, and eventually you have a sudden catastrophic failure of your rope. And in doing so, we were able to show that it was not to do with necessarily the way that this had been designed or manufactured, but the way it had been operated. It is important when we do our work to consider about how to better preserve the evidence. So it's very important that, for example, we are involved in the early stages of the claim so that we can carry out a site visit in the aftermath of the event, so that we can preserve the evidence as best as possible, and we can carry out representative sampling of what may have been the issue, so that the laboratory work and the data analysis that you saw before can be carried out. So those are some examples of how corrosion and metallurgy can be of help in claims for the marine world. And if you have any questions on these types of claims, please feel free to write some in the side chat. While you do that, I'd just like to introduce the talk that will be provided by my colleague James Townsend next week. He's a plant pathologist, and I'll be talking about cargo spoilage, but from a very different perspective from what I showed today, as he'll be talking about foodstuff and organic material that spoils during transport. Thank you very much.
Thank you, Giuseppe, for that interesting presentation. So 4 questions. I'll just start us off with one which we had submitted ahead of the webinar, which is, how do you differentiate between corrosion caused by natural degradation and that accelerated by external factors like grounding or poor maintenance?
Yeah, thank you very much for the question. It is one that we get asked quite often, because from an insurance point of view, it's very important to try and understand whether the phenomenon that we're looking at is an event connected to an event, or is a general corrosion which might carry a completely different weight when it comes to insurance claims. There is a number of ways that we can understand what has happened and how it's happened. Part of it is, as you would have seen in the first case study, is establishing a timeline, try to understand when the different events occurred, and you do that by speaking with the people that have been involved with the event. But there is also a lot of hard data that can be obtained by looking at the type of corrosion itself. So, for example, the propeller hub on the first example, that was clearly a type of corrosion that was localized, and that could have only occurred if that sealing phase had somehow been twisted. And therefore, that was consistent, for example, with the event of the grounding that would have impacted the propeller hub, slightly getting off its axis and allow water ingress in. And then there is the metallurgical inspection itself, so collecting the data, looking at them in the lab under the optical microscope, that can really help look at what phenomenon has been going on, and that alone can tell us if it's something that it is expected as normal wear and tear, or something that may have been due to the actions of somebody.
Perfect. Thank you for that. I can see there are a couple of questions that have come through in the chat as well. So the first one is, do you ever obtain water samples from the ports to dispute the owner's claim?
We didn't do it in this case, but it is something that we have proposed in the past. So far, in my experience, that has never been necessary. But certainly is something that we suggested, and is something that is particularly representative if we get involved early on. Because as you can imagine, if we get involved by the time the vessel is at a different dry dock and has moved completely from the port where the issue may have occurred, that water may have changed as well. So unless it's due to the specific chemistry of the water, we might not be able to replicate, say, a spill, because there was an oil tanker nearby that spilled somebody into the port.
Will make sense. And then there's one which is can loading goods, I think screws specifically, in wet or humid weather cause them to rust during the ocean transit in a container? And I think they mentioned in this case these screws were packed in boxes which were also moldy.
Yes, so depending on what the screws are made out of, normally they would be all galvanized, so there'd be a sacrificial layer on the screw, but it's not one that you would want to perish during transport. Normally that layer is there so that the screws can be used for a long time in the final application. So yes, that can happen, but it ought not to happen, and there are several ways that you can package your material so that does not happen, even if there is salt spray, seawater contamination.
Perfect. And then there's one more that's come through, which is, can hull corrosion be caused in dry dock due to the atmosphere?
In theory, yes. But in dry dock, normally you are carrying out repair, so you're doing something to ameliorate the situation. I suspect if that is happening is because the vessel is left in dry dock for a disproportionate amount of time. Because after you do your repairs, you need to carry a weld repair of a portion that has corroded, like it was the case in that example I provided. Then you would coat the hull, and you would repristinate the ICCP, the corrosion protection. So if that is not happening, then corrosion could occur. Yes.
Great. And there's actually another question that's come through now, which is clearly there needs to be a consistent current to protect. Sorry, I might be misunderstanding. Clearly there needs to be a consistent current to protect. Why don't the shipping companies have alarms if the currents drop above or below the control limits?
They do, which is, but we operate under the assumption that all crews understand exactly what that means and how to rectify, and would alert who needs to be alerted promptly. And that might not be the case. There might be commercial pressures for completing a voyage prior to do an inspection. There might be commercial pressure to wait until the planned dry dock inspection rather than do another one, because they are very, very costly. I mean, depending where you are in the world, but regardless, they are quite expensive events. And they normally even have a feedback system. So once you basically are kept in that between the higher and the lower threshold, so you'd kept protected, but things can malfunction, and then we are left effectively with the human intervention, and that is not always perfect.
Great. And then if we just go back to the question about the screws, if you remember, so
Yeah.
they've just kind of specified a bit. So they said that they meant if the rust or corrosion can be caused by loading in wet conditions, when there's no access to salt water and the container is in good condition.
So if the contamination is due to, say, rainwater or other sort of water, not salt water, I mean, I am assuming if you are doing the loading in port, you still will have some potential salt spray, but say that is not the case. Yes, you can have corrosion just with rainwater. There is a number, of chemicals that might be around that might exacerbate things if they've been at the beginning. I think the first question mentioned moldy conditions, so probably we have wet conditions, stagnant water, and then we can even get microbiologically induced corrosion, so we can get sulfur reducing bacteria that can cause corrosion. So yes, absolutely can happen, and normally there would be a number of things we can do to avoid this when a cargo is loaded.
Great, thank you for that clarification as well. And we'll take this one final question, which is there any paint available that will guarantee no hull corrosion on steel hulls?
So normally you get 3 layers of painting applied, and these days is a very good quality paint. But when you are dealing with a vessel that is seafaring, that is constantly at sea, paint alone will not cut it. Also, say that in port or for whatever reason you get a scratch into that paint, if you were relying solely on the paint rather than the impressed current as well, what you create there is an area that is preferentially attacked compared to the rest of the hull, so it would corrode very, very quickly. So in terms of kinetics, you actually find yourself in a far worse scenario than if you had no paint at all.
Interesting. Okay, perfect. So I think we'll wrap up there then. No more questions coming through. So thank you again, Giuseppe, and thank you everyone for the questions and for joining. Just so everyone knows, a recording of the webinar will be sent out later today to everyone who signed up and will be available on our website as well. And we look forward to hopefully seeing you again in a couple of weeks for our next webinar in the Marine series. Thank you.
Thank you.
Thank you very much.